Hello everyone, my name is Bonnet Romero and I'm excited to present my final project for CSE212, Programming with Data Structures. Today I'll take you through three fundamental data structures: queues, linked lists, and binary search trees. These are fundamental concepts in computer science, each with unique cases and implementations. I'll share examples using code I've written and explain how these structures work behind the scenes. Let's dive right in. First, let's talk about queues. A queue follows a first in, first out, or FIFO structure, just like a line at a store. The first item added is the first one to be removed. The InQueue method adds an item to the back of the queue, and the DQueue method removes the item at the front. Here's how I implemented a queue in C#. Here is the InQueue method. First, I created an InQueue method to add items to the queue. Then I called the method to add three names: Chris, Daniel, and John. When we print the queue, the names appear in the order they were added: Chris, Daniel, and then John. Here's the DQ method. Next, I created a DQ method to remove the first item from the queue. Calling this method removes the first person, Chris, and we're left with Daniel and John. Queues are great for tasks like handling requests on a web server or managing print jobs in a printer queue. Next, let's discuss linked lists. A linked list is a sequence of nodes where each node contains a value and a reference to the next node. Unlike arrays, linked lists can grow or shrink dynamically without resizing. Linked lists have two key components: the head, which is the first node, and the tail, which is the last node. We have two examples here. First, we have a singly linked list. In a singly linked list, each node points only to the next node. And the second example is a doubly linked list. In a doubly linked list, each node points both to the next and the previous nodes, allowing traversal in both directions. Here's an example of adding nodes to a linked list. First, I created a method to add nodes to the end of the list, and then I called the method to add integers from 20 to 70. The flexibility makes linked lists ideal for scenarios where you frequently insert or delete elements, such as implementing stacks or queues. Finally, let's explore binary search trees. A BST organizes data hierarchically, making searches, insertions, and deletions efficient for stored data. In a BST, each node has at most two children: the left child, which contains values smaller than the parent, and the right child, which contains values larger than the parent. BSTs are great for managing hierarchical data, like a leaderboard or a dictionary. They also have levels or heights. For example, this tree has a height of 3, with the root at level 0 and the leaves at level 3. Let's count the levels. Starting with 5, we go to 6, and that is level 1. 9, level 2, and 10 is level 3. I created a binary search tree and inserted several integers: 5, 10, 20, 8, 12, 17, and 25. When we print the tree, the values are displayed in sorted order: 8, 10, 12, 15, 17, 20, and 25. We can also find the minimum and maximum values in the tree. In this case, the minimum is 8 and the maximum is 25. We can also search for specific values, such as 12 or 22. We would receive a true for a search of 12 and a false response for the search of 22. Another operation we can do in linked lists is to display the list in reverse order by traversing the list backwards. Now let's look at balanced and unbalanced binary search trees. A balanced tree has nearly the same height on both sides of the root. Specifically, the maximum difference in height between the left and the right subtree is no more than 1. Balanced trees are more efficient for operations like searching as they maintain a relatively low height. Even if we remove any one of the level 3 nodes, it would still be considered a balanced tree. In contrast, an unbalanced tree has a significant height difference between its left and right subtrees. For example, this unbalanced tree, all the branches extend to the right side of the root and there are no nodes on the left. This increases the tree's height, making operations like searching or inserting less efficient. To recap, we've covered queues, which follow a first in, first out approach for task management. Linked lists, which offer dynamic resizing and efficient insertions or deletions. Binary search trees, which organize data hierarchically for quick searches. These data structures are foundational in programming and play vital roles in solving real-world problems. Thank you for watching. If you have any questions, please feel free to reach out.